Hello, Sambil, everyone. Today we continue to look at HCIA-Storage. In the last class, we talked about the first part of the data writing process on solid-state drives. That is, when there is no data. On any of the drives, what kind of writing method do we use? Today we will continue to look at the writing process. After the previous session, our drives already have a lot of data, right? So at this point, after some data has been written, what happens next? For example, users might delete certain data, right? Or they might free up space to write more data. During this process, some data in certain blocks may become invalid, or it may become outdated. So here, first of all, from the user's perspective, if they want to write new data, they must delete some first, right? After freeing up space, they can proceed. It's like when your room is full of stuff, right? If you want to add new items, you definitely have to take out the old ones first before putting in the new ones. In our solid-state drives, when users delete and write data, it causes the data inside to become invalid or become outdated. So everyone needs to pay attention to this. First of all, we still have 0 to 7, 8 channels in total, and each channel corresponds to one block. In the image here, we use green blocks to represent valid data and red to represent invalid data. First, let's take an example. Suppose we have a host page that starts, which is stored in one of our spaces, stored in one of the locations in our space. The mapping relationship is from A to this specific physical location. Okay, this is a premise, and the mapping relationship here is essentially an address label, which is where the main controller of our solid-state drive goes to find the corresponding host page. Later, after the host rewrites this host page, because our flash actually cannot be overwritten. We mentioned this earlier, right? This is a main characteristic of solid-state drive storage, which is different from traditional hard drives. With traditional hard drives, you can directly overwrite. But with our solid-state drives, you need to erase first and then rewrite. You need to erase first and then rewrite. At this point, if you don't want to erase, you can only look for a location inside the solid-state drive that hasn't had any data written to it. There are two methods for this. One is to erase, and the other is to write again in a place that hasn't been written to before. This is also possible. It's also possible. Two methods exist, of course. If your entire drive is full, then in this situation, you can't just erase or randomly find a spot to write to, because once it's completely full, to write new data, you must erase first and then write. Here, first of all, inside our solid-state drive, you actually have to find a spot where no data has been written. Suppose, here of course everything is already green. Suppose in this section, the second block here, there is an empty space where we can temporarily write data. After writing, the content in the old location will become what? It will become outdated. It becomes outdated and invalid. Here, it's equivalent to before we made modifications, our data corresponded to, for example, this block. After modification, because if you want to change the original content, you need to erase it first, and then write again. If you don't want to erase, you find a new place to write it again. In this way, our mapping relationship changes from the one on the left to the one on the right. That means our physical address has changed, but the logical address remains the same. After the change, the original physical address actually becomes invalid. There is data inside, but the data is useless and meaningless now. This is equivalent to, hey, moving something from one cabinet to another. After moving it, right? The contents in the original cabinet, right, are actually already invalid. The contents are invalid. This is one of our examples. The process of modifying data on a solid-state drive, to be precise, is not simply writing. When the solid-state drive is empty, there isn't much of an issue. Nothing major to be concerned about. However, during subsequent modifications or deletions, this is a point we need to pay attention to. Points to note. Here, as our users continue to write, and our storage space will become smaller and smaller until it is exhausted. Once exhausted, in this situation, those old data actually belong to what we call invalid data or junk data. If these data are not cleared in time, our host will actually be unable to continue writing, and users will be unable to continue writing. So here, in our solid-state drive, there is a set of recycling mechanisms, a garbage collection mechanism, where the main controller of our solid-state drive will periodically scan each block. It identifies those blocks containing a large amount of invalid data and then migrates the valid data to a new space. What does this mean? For example, you can see that in our current 8 blocks, there are both valid and invalid data, right? If you want to erase a certain specific block first and foremost, you need to move these green valid data to another disk or another block before proceeding. Once everything becomes invalid, you can then proceed to erase it, and after erasing, this block can be used again. This is something to be mindful of when writing data. Secondly, in the previous lesson, we mainly discussed the situation of writing on a clean disk, a clean solid-state drive, but here, if it has already a lot of data written to it, and it's already full, the subsequent processing methods involve the solid-state drive periodically scanning and consolidating useful data together while uniformly erasing the useless data. Here, although our garbage collection mechanism can solve the space issue, there are also some challenges. For example, frequent garbage collection operations can increase the write amplification phenomenon in solid-state drives. Write amplification actually means that the amount of data actually written to the solid-state drive is greater than the amount of data the user requested to write. What does this mean? Originally, I only needed to write, let's say, 1 GB of data. Originally, writing it in one go would be fine, no problem. However, if you later need to erase a certain block on the drive, at that point, some data in that block will be rewritten to other blocks before erasing. In this way, you are essentially rewriting a portion of it, though not all of it. However, this will definitely be much larger than the original write size. Each time you erase, you have to rewrite, and each time you erase, you rewrite again. This is actually a major issue. Drawback, this is the main drawback here. The higher the write amplification factor, the heavier the write burden on our solid-state drive. This will also affect the performance and lifespan of our solid-state drive. So, in order to reduce the write amplification, our main controller also has some optimization strategies, such as the management of the mapping table, reasonable mapping table management, and intelligent garbage collection scheduling. In addition, the management of valid and invalid data states in our solid-state drive also involves our TOI, flash translation layer technology. As we mentioned earlier, it is essentially our translator, responsible for converting the logical address of user input data into a physical address. During the process of writing, i.e. updating and deleting data, our system, the flash memory will update the mapping relationship in real time to ensure data storage and access, ensuring the data policy storage access. From a practical application perspective, when we use computers daily, including mobile phones and other storage devices, we are actually dealing with data writing on solid-state drives, right? Your phone, right? There's no need to say more, right? Wait, it's impossible to have a mechanical drive in a phone. As for computers, many of the newer models now come with solid-state drives, and it's rare to find one with a mechanical drive. Overall, the performance of mechanical drives is rarely sufficient to meet our daily needs. Storage isn't an issue, but for other daily activities, various types of work, and entertainment-related tasks, mechanical drives are hard to satisfy those needs. So currently, it's basically all solid-state drives. So in this context, everyone should pay more attention to the usage of solid-state drives in their daily lives, including aspects like lifespan. You can regularly perform disk cleanups on solid-state drives, reduce junk data, and free up system monitoring space, among other things. These actions can be helpful and provide some benefits. Alright, this concludes the content of our lesson. If anyone wants to learn about this technology from Huarun or wishes to obtain the Huarun Certification Question Bank, please send me a private message or leave a comment below the video for technical exchanges. Okay, that's it for today.